the board meeting over the next 2 weeks. I was feeling a lot of pressure about this talk because I have to summarize what all of ECCO is. Then the Chiro gave his excellent mathematical talk, so I don't have to do that. And then Luann gave an excellent talk about the application of ECCO, so I don't have to do that. Just kidding. We have 2 weeks to talk about what ECCO is, so at the end of this talk, you probably won't fully know what ECCO is, but you'll have a good start. And we'll continue the conversation over the many hours we have together. So I started working on ECCO when I was a graduate student. Carl was my advisor. Patrick was a co-advisor. So like other people, I drank the ECCO Kool-Aid. I thought this was the coolest thing we could do to combine these satellite observations and in-situ observations of the ocean with the state-of-the-art, fully global ocean simulation. So I've been working on this project ever since. So I'm a big believer. I hope my enthusiasm for it comes across, and you guys also get some enthusiasm for it. I came to JPL after my PhD to work with the oceanographers and the ice folks over there. So at JPL they have a strong ice sheet remote sensing group. And since ocean ice sheet interaction is a big topic, I thought it would be a great place to combine what we had already done, my background in kind of like high latitude oceanography with the ice sheet work. So now at JPL I work on a project, I work on ECCO, and I also work on another project called Oceans Melting Greenland, or OMG, which is a NASA-funded field program to collect in-situ data around the Greenland ice sheet, to collect ice elevation data with the airborne radar, and to use sonar to collect the seafloor bathymetry data. So that's a really cool project too, and it has nice tie-ins with ECCO. Because how are we going to use those observations that we collect, heterogeneously in space and time around the ice sheet in the ocean? Well, the answer, of course, is to use kind of the ECCO framework, which is now what we'll talk about. Okay. So ECCO as a name, of course, we all know what it is. But there are many products that have the ECCO label. So I'm going to survey some of them and emphasize the one that is what we call the central production, kind of like the main best fit to the ocean data that we have. And I'll also talk about at the end some of the tools that we developed and used to analyze the solution. And some of those tools we'll all have a chance to use in the hands-on sessions in the afternoons. So the ECCO consortium is many people scattered across many institutions. And we were just talking about adding Woods Hole, because Chris Pykush is now at Woods Hole. We don't have Woods Hole on the list. Yeah, right? So people who work at different parts of it over many years. Right? Some institutions are new on the list, like Texas, right? Relatively new, Woods Hole. Yeah. Some have been there for a while, like Scripps and MIT and Hamburg. They've been there for a long time. So there's many people working over in many institutions. The core of the ECCO central production work these days is sponsored by NASA. So it's a NASA product, and we really have Eric Lindstrom in the back to thank for the support. So a lot of terms are used when we describe ECCO state estimates. Okay? ECCO state estimates are physically consistent solutions of free-running ocean models that are made consistent with observational data and their uncertainties. It's like some jargon in there. I'm going to unpack it. Okay? State estimate, physically consistent solution. What do we mean by physically consistent solution? Does anyone know what we mean when we say that? When ECCO people say that?
Closed budgets.
Closed budgets. That's one thing we can do. Definitely as an aspect of it. Sure. Yeah, it's not wrong.
So does it mean that it captures resolution or matches?
It does not mean that. Yeah.
It's a solution in an average Stokes equation?
That's Very good. Slightly imprecise, but yeah. Because something that your Stokes equations.
It's a solution of whatever you can present in this model.
Yeah, as a more general and slightly more accurate answer. Yeah, so it's a solution to some equations. So Eric teasingly said Navier-Stokes equations. You know, it's not quite the full Navier-Stokes equations, but it's a what we have is an ocean model, right? We have the MIT-GCM, and the MIT-GCM can run the model forward, right? And for 25 years, you get a solution of the ocean circulation on planet Earth. Something that looks like the ocean circulation on planet Earth, if you give it the right atmospheric conditions, and you give it the right initial conditions. So this model is capable of simulating lots of different, what we can call realizations of the ocean circulation, right? So it could like be anywhere in the possible interannual variability of Earth's oceans, modern oceans. So one of those solutions might look like what actually happened, right? One of those infinite number of solutions the model can give you actually, more or less fits what actually happened. We want to know, we want to find that one. Or we'll never find that one. Or we want to find one that's good enough. Some analogs. Some analogs in life here. We want to find one that we think we can settle down with. Throw it all together. We want to find one that's good enough. And what do we mean by good enough? All right, what do we mean by good enough? We mean one that matches the data to within, in a way which is consistent with the uncertainties of the data, right? There's some observations I can make of the ocean with a really crummy thermometer, say, and then I'll say, please give me an ocean state estimate that matches all of the data everywhere perfectly, right? And so that for you to match that one crummy observation somewhere, you know, would be a mistake, right? So hopefully, if you know what observations, what their uncertainties are, it can guide you in a least square sense to like know which ones to kind of ignore, which ones to pay more attention to, where to pay more attention, where to kind of let it go. And this is schematically represented here. So one of the many possible solutions to the ocean model is that red curve, right? Totally legitimate solution. Like no one would ever no one could look at it and say, no, here you're not conserving mass, or here you're not conserving energy. Red is a perfectly legitimate solution, but it doesn't match these schematic observations within those bars which we drew, which are the error bars. Okay, some statistical sense. So after we make, right, waving my hands here, make the solution consistent with the data, we get the blue curve. Okay, this is a solution. It doesn't like perfectly match the middle of every observation, but it's within those error bars. Okay, and it's that blue thing that we call a physically consistent state estimate. Consistent with the equations, and it matches the data.
Yeah, so that's the MIT-GCM solution that follows the Navier-Stokes. Where does it lie? Or where does it lie in this graph?
It is the model is the thing that when you run it, it gives you the blue curve. So blue here is some state, some measure of the state.
So like first assuming kind of the initial condition for.
Yeah, okay, exactly. So now we'll get to that perfect transition. How do we get from this red curve to this blue curve, right? This is the magic that we're all going to learn about. So Ichiro actually gave you the answer this morning. Right? It's like magic. No, it's underlying all of this is a very rigorous mathematical basis. Okay, but in practice, what is this problem? How do we get there? And okay, let's think about what we mean by the model solution. So the model, when you run the model, what do you have to specify? You have to specify some initial conditions of the model, and then some forcing. So we have an ocean-only model, Nguyen said. Ocean-only model. So ocean-only model means we prescribe atmospheric state. In our case, we prescribe the atmospheric state. So right, we put atmospheric state over the ocean. The bulk formula gives us some flux, okay? We have initial conditions with some atmospheric state. We also, these days, have some unknown unknown subgrid scale parameters, right? For example, Gent McWilliams mixing coefficient, kappa, right? So we can use a single value for this kappa, assuming that it's the same everywhere, but it's not, right? So we say we don't know what kappa is everywhere. It's an unknown. Okay, so we have to say these three categories of things: model parameters, atmospheric state, initial conditions. Some combination of those three things together will get us the red curve, and some combination of those three things together will get us the blue curve. Okay, the problem comes down to an inverse problem. We want to solve for the initial conditions, the atmospheric boundary conditions, and the model parameters that get us a solution that falls on that blue curve, or gets us a blue curve-like solution. Okay? So that's what we mean by physically consistent. This is what we mean by consistent with observational data. It's within the error bars. And the way we do it is we formulate an inverse problem. We solve for the model initial conditions, the atmospheric conditions, and ocean mixing parameters to minimize the model data misfit in a least squares sense. So when Achiro kept saying, this all reduces to least squares, that's why he was saying that, right? In Carl's book, every chapter is, this is least squares, right? I recommend that you spend a lot of time with that book. But that's this whole point. It's a least squares problem. This is the thing we're trying to, these are the squares we're minimizing. And how we get there exactly is a choice that different people within ECCO, the ECCO family, choose. Okay? There's one approach called the adjoint method, which we'll learn about later. There's one approach called the Green's function method, which we'll learn about later. There's another method called Kalman filter smoother. All right, you may have heard of these terms. So these are three different ways of getting to that blue curve. All come down to least squares, but different methodological approaches based on convenience, size of the problem, and other factors. Okay. So we're on the same page now, because I felt like maybe this hadn't been explained yet, so I added this much. Okay. So let's talk about the physically consistent part of this. There are many ocean reanalyses products, many atmospheric reanalyses products, many things you can go and download that give you like monthly fields of TMS over the planet, not just ECCO. Right? Almost all other solutions are of the class, of this kind of class, of a sequential filter. And what does that mean? It means that, okay, that's not really very accurate, because I think the Argo products are not filters in a sense. But other solutions are like the red solutions, okay? And the reason I put the schematic up here is to illustrate the point. When we come up with a physically consistent solution, this time axis for ECCO is just for our central production is like 25 years, okay? Many other kinds of products have free-running solutions, but the time window of that free-running solution, it might be just 1 month, or it might be 1 day, or it could be 6 hours, right? It could be very, very short. And then something happens. At the end of that 6 hours, or 1 month, or whatever, some new data is made available. The model has evolved from here to here. New data is made available, blue circle. And then there's something called assimilation of that data, which you do some least squares. And you say, I'm gonna change my model state to fit this data. So literally the state of the whole of the model is changed. So it was 1 degree in this spot, and then all of a sudden it's 2 degrees. Where did the heat come from? Where did the energy come from? Doesn't matter. It's just now 2 degrees because now you observe something that said it should be 2 degrees. So then you end up with this kind of solution, the red solution, which can be useful, but it is for many purposes, but it is not what we do, and we prefer the blue one, right? So you can generally get a better fit to the data with the red, because you can kind of make the state whatever you want. But then you can't do certain things like do closed budget calculations, because in those solutions, heat just appears, right? You can't say, I went to a talk, a guy was talking about moisture budgets in the Arctic, using an assimilative modeling of this. So in that model, moisture would just show up in the Arctic. And he was trying to calculate where it was coming in, meridionally. It's like, do you even realize that your solution just makes up moisture? You can't do it, you know, because anyway, so we prefer the blue. We prefer the blue. I've used the red. You guys probably also use the red all the time, right? But we make the blue. Has to be said. Someone has to say. Okay, so we have several products that I'm going to talk about, and then analysis of this. First one is what we call central production. We're all clear, I think. We're all laughing. People are like engaged, so I think people are on the same page. Okay, very good. Okay, so we have this thing called central production, and it's the thing, one of the solutions, one of the blue curves, I guess you can say, that is we're very proud of, and it's what we call the flagship ocean state estimate. So it's generally speaking our best reconstruction of the global ocean. Avi.
Is that understood with your first slide where you talk about the first phase and optimization?
Yeah.
Could you go back again?
Oh yeah, okay.
So here the first gas is depend on the model ocean model output. And these also depend on the ocean, like atmospheric state and initial condition and parameterization and change the materials and some other things. So I'm thinking rather than choosing the first gas from the ocean model, why do you not choose from the real analysis product?
Well, the first gas we are very careful about what we pick as the first gas, because we want this problem to be easy. We want to be as close as possible. We don't make our first gas temperature 25 degrees everywhere. We make our first gas something, actually, like traditionally we use climatology. And in these days, we've been doing this for so long that we make our first gas our last best first gas. You see? So we always have like somewhat good starting point. Yeah.
I'm thinking that the ocean model is like, they have too many parameters to do, so more chances to have this spread rather than if you put just the analysis for it very close to the observation.
Oh yeah. In a sense, we do. We pick something as close as what we think is right as our first guess. But inevitably, even if you had a perfect knowledge of the initial conditions of the ocean, you know what you don't have? You don't have a perfect representation of the atmospheric state. Because every reanalysis product, no reanalysis product is perfect. And no bulk formula that we have come up with is perfect. So you need to make some, you need to help it to steer the ocean in the right, to do the right thing. Right. Also, we don't know these kappas everywhere, right? We have see, we don't know these things, so it doesn't matter really what that first guess is. I want to make one point. These error bars that I have drawn up here, we also have them for the atmospheric state, the kappas, and the initial conditions. It's not just the model ocean observations that we're fitting. We're also fitting the whole thing. We don't want to just allow arbitrary changes to the atmospheric state. It's like that X transpose S X term from this morning. A regularization term. You remember that one. we have the smoothness constraint, for example. We don't just like, if we're gonna put in a storm that wasn't there, we don't want just like the winds on one 6-hour snapshot at one point to be 100 meters per second in the opposite direction of the adjacent wind field. So we put that in, we built that in. But we can talk over many coffees at length over those details. Okay. So essential production run. Currently we're in something called, we're in version 4 of this. Here's a timeline of all the different versions. The earlier ones were like almost single-handedly, I would say, made by Patrick. So here, Patrick and friends, but I think Patrick did almost all of it. So we had the earlier versions of ECCO, and when I started, we were somewhere here in version 2, I kind of remember. And one thing about those is that they were coarser. They were 2, 3 degrees, or what was the first one, Patrick? I always ask you.
The very first 0 is 2 degrees.
2 degrees. And then they didn't have an Arctic Ocean. They had a wall at 80 North. I remember that. It was surprising. And then, because there was no sea ice model, it was just an ocean model at the time. And then they added a sea ice model, and we added the Arctic Ocean. The grid changed. Now it's about 1 degree grid. And that's where we kind of are now. We finished this last release in 2017, 2018. And it's a 1992 until 2015 solution. At JPL, we're putting the finishing touches on the solution that goes until the end of 2017. Why did we start in 1992? Because that's when the real satellite altimetry from Poseidon became available. That's our starting point. The idea is that before then, there weren't enough ocean data to constrain this well enough. Even with ships, I mean, people do it, but the philosophy at MIT, I guess, in scripts was let's do it now that we have Topex. That's where we start. And ECCO version 4, release 3 is, like I said, about 1 degree. It includes the full globe and has ocean and the active sea ice. We have a version 5, and at the end of this calendar year, we'll have version 5 will be officially released. Right now, you can get it on the website. It's called ECCO version 5 Alpha, and it's 1/3 of the degree. Okay. This one, you're going to hear this term a lot, LLC 90. LLC 90. Talk about what that means. This one here is LLC 270. Okay. So 90 means like one of the faces of the 4 that go around the planet is 90 grid cells. There are 360 degrees around the planet. 90, 1 times 1 degree. 90, 90, 90, 90, 1 degree. The 270 is 3 times finer resolution around the equator, and things like that. Okay. You'll hear it, remember, like LLC 4320, right? That's what Dimitri runs. 2 degree, 2 kilometer solution, right? But this is LLC 90 and LLC 270. Okay. So when we make this state estimate, we make that blue curve. It's, like I said, a full model output. So when we run the model, we save fields. Right? We want to know what the state is. And here is a list of some of the fields that we make, that we save, that we make available to everybody. So with the ocean and sea ice state, of course, we have temperature salinity, we have the velocity vector, we have the sea surface height, we have density, and we have bottom pressure. Sea ice, we talk about this concentration, the thickness, the snow thickness, the snow velocities, the sea ice velocities. And then, of course, importantly, we include all of the terms that you need to close the budget. So in any model grid cell, finite volume model that we have, there's a time evolution equation, a prognostic equation for temperature and salinity, right? So you have the left-hand side, ds, partial s, partial time. And the right-hand side, everything that when you add it together, it changes this temperature or salinity. So we include all of the terms on the right-hand side, so that anyone can take a box and determine which fluxes of heat and salt and mass or volume were together combined to give you the state that we make. And when Luann was talking about Martha's budgets, that's what Martha did. Martha Buckley took those flux fields, all of these right-hand side of the equation fields, drew a big box, right, in the North Atlantic, and then added up all of those terms and then analyzed them. Chris Pykuch has several amazing papers where he does that same kind of thing, and then does more clever analysis on those terms, trying to figure out why was the effective heat flux in this spot higher this year than that year. So that's what we include. You'll see them all later on. Atmospheric state, we mentioned that we have a first gas atmospheric state, and we solve for adjustments to the atmospheric state, corrections, if you will, of the atmospheric state. So this corrected atmospheric state is formally part of the solution, so we include that too. The state and the fluxes, and air-stream fluxes, and then I mentioned before these subgrid scale parameters. So we have the solution, we give it to everybody in two different forms. The first one is the form that everyone understands, is the interpolated onto a lat long grid form, right? So this is the one that is obvious to everybody. And it's cool, right? But not useful for some things. So useful for some things, not useful for other things. What is it not useful for? You cannot use that interpolated grid to close budgets, because the budgets are the model solves its equations on a curvilinear grid whose grid cells are not lined up with meridians or parallels and meridians everywhere. So some of the grid cells are like rotated in space because we live on a sphere, and so we have to do that. Okay, so the grid cells are oriented however they are. So we have grid cells oriented however it is, and we have fluxes that are pointed in whatever direction those boxes are pointed. So if we try to interpolate that onto a lat long grid, you lose something, lose a little bit. So we also provide the solution on what we call the native grid, and it is a decomposition of the Earth into 5 kinds of pieces, or no, 2 different kinds of pieces. The first kind of piece is the Arctic cap. It is the reason why we call it cap, and why it's LLC cap, Arctic cap. And the other 4 pieces of this beach ball are almost lat long grids. And if you break it all out, it looks like this on the bottom. Okay? So each of these faces on the side are broken into 3. So we have the Arctic cap. It's 90 grid cells by 90 grid cells. And then you take all these pieces and you line them up, it looks like this. So 90 by 90, they're all 90 by 90. Okay? And this is kind of how they're oriented. The model has an X direction and a Y direction. Sometimes the X lines up with east-west, sometimes it doesn't. So when you plot the tiles X, it's like this, and the tiles Y, it's like that. That's why I show it in this kind of fan. Don't worry. We'll get to all that later. Okay, so what are the data that we use to constrain the central production? What we don't use are tide gauges for reasons that were debated very much. But what we do use are about slightly less than 1 billion other observations from in situ platforms, seal platforms, from space-based platforms, from airborne platforms. Here is a list. We include sea ice and sea ice data. Of course, we use GRACE. We constrain to a climatology, we have a dynamic topography. We constrain not just to altimetric long track sea surface height, but we also constrain to the global mean sea level and the global mean ocean bottom pressure. So altogether, slightly less than 1 billion observations. And each one of those observations has an error bar. Okay. So it's actually this many data and the equivalent number of error bars.
Sorry.
Yes, sir.
Are some of those observations pre-processed before to be applied to the acoustic estimate?
That's a great question, right? Because think of a satellite remote sensing platform like an altimeter, right? What it measures a 2-way return time. Right? We use somewhere down the line of processing when that data becomes a geophysical parameter. So for altimetry, for example, we use, I think they would call it a level 2 product, a long track, right? For, similarly for grace. Now, grace is a naturally a gridded thing because it's on, just by virtue of the way it's observed. So in that case, it's a level 4 product. It's a gridded product. For SST, we use a gridded product as opposed to a long, a swap SST.
And then for Argo profiles, for instance?
Argo profile, we use the profile itself. So yeah, we don't use a Thermic and Gilson. Yeah. Yes, sir.
Is it fair to say that this is all scalar data? There's no vector data assimilate?
Correct.
Will anybody explain why it's so difficult to assimilate vectors?
It's not difficult. Vectors is just a multiple component scale, multiple scales.
Then why are current meter data not assimilated?
Because there aren't that many current meter data to warrant us to include it
Okay.
until other data are included.
They're like tide gauges.
But I would say that
Yeah.
drifter tracks, they are not assimilatable because the tracks are chaotic. And they are a result of things that we do not resolve in the ECCO model, like at this resolution, or any model, even at 4320, we're not going to resolve that. And that has to do with what Patrick mentioned, representation error. And we can talk about this perhaps at another time, but another.
I think Anne might be taking some stabs at it, right?
No, I think the Arctic state estimate, we are using the current meter for the mooring because some of the important gateways, those are very strong constraints. So the framework is there. I think it's just a matter of global versus regional, and if you look into the contribution of the weights to see, or you look into the contribution of the data set to the entire global data set,
Okay,
and how much it can contribute.
got it.
Yeah.
Can I
Yes.
just ask, when you assimilate the current meter data, do you average it in time first, or?
We do it in time daily average at the moment. So first of all, because we don't represent the Thai, so first you have to get rid of it, and then of course you have to, there's no reason for us to try to fit it to every our
It's the age matrix, right?
Same thing applies with data, other data too, for instance, altimetry data. At the GDR, so-called GDR, that 6-kilometer resolution. At this kind of 1-degree resolution, there's no sense in trying to constrain the model at 6 kilometers because our grid spacing is 100 kilometers. So we average out a long track to a much coarser resolution. So we decimate the data in essence before using it in constraining, because it's just a waste of memory space to handle all that data, which we can't use. The information we can't use.
Yes, sir.
So you're not assimilating the microwave SST?
Correct. Not the, okay. In the sense that our SEC product is a VHR.
Right.
Yeah.
I mean, would there be any value to doing that? And
Yeah, actually, yes. And we are.
We have actually the version 1, we have assimilated the microwave data, but then we found, at least in the data that we had, there was an inconsistency between the microwave data and the Reynolds SST, and they led to spurious effects of changes in SST trends, and they were also not matching. So we stopped that until we get we were under the assumption that
GRIS would help.
GRIS,
Yeah.
well, then we were under the assumption that GRIS SST would have a merged product that would be exactly like, when we think about altimetry, that's basically an intercalibrated product across all the satellites. And at least the data that we used for the SST, we found after the fact that that was actually not the case. So it might be today. So this is sort of established about 2013, 2014. And so so basically we held off. But it's totally, there's nothing that stops it. It's basically just to make sure that we have data sets that are not contradicting each other too much, right? They can contradict each other because we deal with contradiction with the uncertainty estimates in each data set, but if these are systematic contradiction, then there's something wrong.
Well, I want to say that we're going to have a project, access product. We're working with Kodak to use GRIST, which includes products that are from microwave SSD. So it's actually happening now. And another thing is that one of the ways that we include this data is to remove its time mean or its spatial mean, for the reasons that Patrick was alluding to. Sometimes you have satellite derived products that have an offset. Maybe one is collects the data, and one geophysical transfer function has a slight bias for nighttime observations or daytime observations, or all these kinds of things that can just create a small offset. So if you remove the means and you constrain against the time varying anomalies, it's another way of using the data without having to worry about trying to square the circle.
Yeah, I'm just curious about the assimilating things like Grace or Aquarius that are relatively short compared to the whole record.
Yeah.
And how does that help the solution? And to do it just with part of it. I'm just kind of curious how
I'll give you an example.
How that all works, and then why you would not include other satellite sea surface salinity products that are non-overlapping.
I'll give you an example answer for one part of that. There's lots to unpack. But take urinalysis precipitation field. Some urinalysis products precipitation field. What if it has a systematic bias so that it's raining too much in the ITCZ, right? So for 25 years of a solution, we don't have any sea surface salinity data. Maybe we never know that. But then we include the Aquarius data, which is maybe a short time window, and we identify that there's a correction needs to be made to the precipitation field in the ITCZ to overcome this reanalysis problem, right? Well, the way that we have formulated our atmospheric corrections, there's like a time mean correction and a time varying correction. So actually the improvements that are made over that shorter window can project out the whole time period. So it's not, otherwise we run the risk of getting a solution that just does whatever it wants in places where we have no data, and then all of a sudden where we have data is down here, and the data goes away, and then the other biases come bring it back up. So we want to avoid that. That's one way to do it. Chris.
There's another part to that answer too, something that you alluded to in one of your first slides, the blue curve, in that even if you don't separate out the mean and the anomalous components of this, you require your state estimate to satisfy the laws of physics. So even if you're only assimilating Aquarius for, say, a 4-year period, that information is propagating through space and time according to the primitive equation. So it does have the potential to propagate and affect the solution outside of that.
Absolutely true. Absolutely true. Yeah, I mean, no, I have to go on. But there's an authentic aspiration to use all the data, right? Authentic aspiration. And there's a realistic, we are a $10 million project, we're not a $100 million project. Evidently, if I can say why we need to be a $100 million project, we can get all the data, right? But there's a limit, right? We work nonstop on this point, like every day, every week, every month, every year. We can handle this much data, right? If you want to help us, you're welcome to. Very welcome. No, so that's not, I don't mean that's a joke. You're very welcome to. Yeah, we would love to have someone who knows a lot about, remember with the SEAL data, right? For the SEAL data, we weren't using it because no one knew any, we were in like Cambridge. We weren't going to South Georgia Island. But then we had a postdoc who climbed up on elephant seals and tagged these things. And then, right? That man came and he was like, we should use this data. And then it sounds like a joke, but it's like once someone knows about the data and how to interpret it and what the uncertainties are, and can point us to the repository, then we can do it, right? I use sea ice concentration data we use it for the first time in my thesis. Maslow, Jake Gebbe, everyone, you got that data. Okay. All right, so be a postdoc with your custom data set, and we'll be able to use it.
I mean, the more general, I mean, that's exactly, I mean, we don't, sometimes we also use data, hopefully, that we don't know about or we connect with people. But I think the general story is, you know, we have to prioritize and it's, to do it well, you have to do it carefully, right? So you have to understand the data, you have to, you know, remove effects in the data that are not in the model and understand that, and then you run the system. You have to understand how and what way the data actually impact the solution. And so, you know, so yeah, take some time.
I'm going to tell one quick story. Went to a workshop in Bremerhaven. Guy was there, expert on tagging the seals, on like tagging the harbor seals, and he said, "Oh yeah, by the way, everyone knows that the proximity of the conductivity cell to the brain of the seal can cause the conductivity cell to give incorrect readings. Everyone," he's like, "everyone knows that." Yeah, I did not know that. Because when you read when you go to the manufacturer of the conductivity cell that they use for the seals, it'll give you an accuracy. But then, you realize that accuracy is in a very controlled environment. And the conductivity is measuring something that's an electromagnetic field. So if anything is in the electromagnetic field that can induce a current, it'll propagate back into the conductivity cell. I didn't know that. Right, but that's what kind of it took.
Can you tell what the seals are thinking by the story? Get this thing off my head.
I'm hungry. So the solution, we have it on an FTP site. We have it on the system that we're all going to log into later. We can see the files.
You're still using FTP?
No, just kidding. Of course we are. We're never going to stop using it. We're putting it on the codec. Also, that's the thing that's happening right now. But FTP, we have it on FTP.
It's going away, doesn't it?
Yeah. Yes.
It's going away by NASA mandate.
Yeah.
We implement a draft thing. It's a draft.
Okay, just so I warn people.
Yeah. Well, we have it mirrored on FTP site with Texas, but anyway. Sorry, well, I don't know. One thing that we include, which is something that we're all gonna get maybe if you want to get your hands on. We have everything you need to run the model, right? To make the blue curve yourself. Everything you need. It's not something like cook it up in the lab, a JPL and everything. Everything that you need to make it, we provide it. So we provide all the initial conditions, the boundary conditions, everything. We can even here in summer school, thanks to the hard work of many of the Texas folks, and you can all run the model yourselves. So that's officially part of what we provide, which I think is super important. There's no way I'm going to be able to finish my slides in the time I have allotted. But that's fine, because we're here for 2 weeks, right? So here's an example of blue curve, red curve. Blue curve, red curve. Left is the red curve, right? It's the first guess. Perfect. This is misfit to in situ temperature data at 3 depth levels. 100 meters, 350 meters, 1,000 meters. Over most of the ocean, this is Argo. Okay, so think of it like misfit, Argo. Seal data at some high latitudes, and of course, those ship was other cruises. Red curve, and then what we plot here is what we call a normalized mystic. I could just say what the misfit is with respect to temperature, model minus temperature, right? But that's not so interesting because we're doing a least squares fit. So like I said, every observation has an uncertainty. And you know a little bit of statistics, you can say well, what we expect, my chi-squared curve, what I want my PDF and my misfits to look like, right? So we expect that the vast majority of my model-weighted residuals will be within plus or minus 1 sigma, right? 99.8% of them will be between plus or minus 3 sigma. Okay, got it. So if we were matching the data very well everywhere, this curve would be green, it would be all 0. And then think of the number here, it's not as temperature, it's as number of standard deviations away from what we think it should be. Okay. So the red curve shows big differences in red and blue. at different depth levels, and the blue curve are fit. On the right is much smaller residuals. Some residuals, of course, still persist. Some of them we'll never be able to fix because some of them are because the model is imperfect, 1 degree model, right? We have an observation on the continental shelf, and we don't properly account for the fact that the model can't do the continental shelf very well, then it's going to show up as a big uncertainty, for example. Yeah, so not only does it match well, which we know many parts can do, right? But also, if you look at the evolution of the solution through time, right? The evolution through time, that blue curve is smooth. Okay. So here I'm comparing the blue curve, our solution, with a red curve, which is the Remick and Gilson hydrographic product. Okay. So Remick and Gilson uses all of the Argo data in a given month and maps it, intelligently maps it onto a grid. Okay. So we expect it to match the Argo data pretty well, because that's what it's made from, right? So that's red, Remick and Gilson, and blue is our solution. So you see, from one, and this is you see Pacific Ocean salinity from 0 to 2,000 meters. Chris Pike made this one. For 2 different boxes that we just made pick these boxes, and the point is, the red curve is according to the data, right? But from one month to the next, you see it can be a bit jumpy, right? Because that's by nature how they construct it. Every month is a good fit, but it's just whatever it is. And whereas the blue curve is smoothly evolving through time, and it is very similar to the data. Okay, this should try to convince you why the blue curve is the cool and fun thing to do. So I'm not going to show any more of these kinds of plots for the ECCO version 4. What I'll talk about now are ECCO family. So I'll talk about 3. ECCO Darwin, ASTI, SOCI, or BSOCI now, and some other regional work. Okay. So recall that I mentioned that we will be doing version 5 of the central production, end of the year, one third of a degree, LLC 270. So 2 of these products use that same model grid. So they are of that same resolution. The ECCO Darwin project, which is led by Dimitri Menemelis, who's here, postdoc Dustin Carroll, and some other folks at JPL, uses the ECCO version 5 experimental setup, and they added into that a biogeochemistry model called Darwin. So ECCO Darwin. And the motivation is partly the ocean carbon problem, right? So we have carbon emissions, total emissions, total integrated emissions in black, right? This is our fossil fuels and cement and everything that we're doing over the last 120 years. And that carbon's going somewhere, some of it's going into the ocean, okay? So ocean is blue. Ocean is taking up a big fraction of the total carbon emission. We would like the ocean model, the ocean state estimate, to tell us how, why, where, when the carbon is going into the ocean. Okay. So because the carbon fluxes into the ocean are highly linked to biology, biogeochemistry, that's why they include this biogeochemical model into ECCO. So, like I mentioned, it uses the LLC 270 solution, and they added this biological component. I'm not an expert on this. You can ask Dimitri if you really want to know. But it added this representation of some phytoplankton and zooplankton. It added a representation of some chemical interactions. We add to the atmospheric state the PCO2 of the atmosphere, right? Because we need to know what the PCO2 is of the atmosphere in order to get the fluxes into the ocean. Right? The model has some additional data constraints that were not on our big table before. Say, for example, SOCOM biogeochemical Argo profiler, super cool. Argo dissolved oxygen profiler, super cool. Some surface flux, I think that's probably buoys, super cool. And the way that, well, let's get how they solve the problem. Here's a nice shot that shows data on the x-axis. This is a scatter plot statistical fit. Data on the x and what the model comes up with on the right. So here's some resolved inorganic carbon. And here, for example, is the most important one. Here are the fluxes. So the observed carbon fluxes versus the simulated fluxes. So the simulated, when CO2 fluxes are calculated, you need to know the PCO2 of the atmosphere and the PCO2 of the seawater. I don't know, well, this is a movie. Well, I never watched it. I just knew it. So the model solves for the PCO2 of the ocean, right? And so we provide PCO2 of the atmosphere, flux is calculated. So here's what the model simulates for PCO2, and here are the fluxes. So that's a cool movie, who knew? And then we can compare, this is really exciting. This is really exciting. We can compare, or rather they have compared their PCO2 of the seawater against other products. Where did the other products come from? Well, how are they made? It's mostly that objective mapping that we talked about this morning, that Achiro talked about this morning, right? Some measurements of some seawater properties, and the calculation of PCO2, and then map it in space, okay? So when you do that in space, of course you end up with problems like you have data gaps, like there's no measurement of PCO2 input variables under the sea ice in the Arctic. Say, for example, so Ito's, Takahashi's PCO2 climatology, which is on the top, is it's missing some points and limited data in the Southern Ocean, but it's what he's got, right? Some gaps. And then you go down here. This is what Dimitri and Dustin have come up with. So it's qualitatively similar, quantitatively similar, and and from that you can get the CO2 fluxes, which also look similar. And this is really amazing. This is a simulated chlorophyll on the bottom, and then on the top is observed ocean color chlorophyll. So from NASA Polymotus, I guess. And you can see just amazing, right? Like the qualitatively similar. I'm not an ocean color guy. I can't quantitatively evaluate this, but the fact that the model is able to tell us, we think this is where there is enough biological activity to generate chlorophyll, and the fact that it matches with the observations, I think is very exciting. So they're also very excited for it. But the most important thing is not just that it gets the fluxes right, is that we can diagnose why the fluxes are the way they are. Why is the PCO2 of the seawater the way it is? Several factors cause the PCO2 of the seawater to change. One is if you change its salinity. One is if you change its temperature. So you can diagnose the factors that change PCO2, make a budget, if you will, of things that cause PCO2 to change, and then break them out, and together with the total. So in the other products, the way we've done it before, you estimate PCO2, you know PCO2 of the atmosphere, and then you calculate the fluxes. But you don't know why the PCO2 is the way it is in the seawater. So like I said, now we can analyze, we can at least take a first stab at trying to figure out why the PCO2 changes it when and where. That's very exciting. So that, yes.
This is the third degree, the echo?
1/3 of a degree.
And that's the one that's coming out this fall?
Correct.
So you're still, the coastal region is still not really resolved?
The upwelling?
Yeah.
Yeah, you know what, I was wondering about that too. My guess is
you
that
don't see that.
you don't see it, right?
Yeah.
My guess is that it has has something to do with the strength of the winds along the coast, because the reanalysis winds along the coast probably aren't strong enough.
Third degree, though, that's.
It's the reanalysis wind product that you're using that would drive you.
No, I understand, but a third of a degree is probably deformation radius-ish.
Yeah, in many places.
Yeah, so it could be either, probably.
Oh, I see. Please direct questions about that too. ASTI, and we're lucky to have her and other people working at ASTI here. So I'm going to very briefly go through this. Apologies in advance. So the ASTI setup was set up to focus on the Arctic and North Atlantic block, all the way to 32 degrees south, and it extends out into the North Pacific. So it's this domain. It's the LLC 270 type grid, okay? And the focus of it is this, really, instead of trying to get the whole globe all times right, really try to get this part of the globe right, okay? So it's one of the reasons that we do regional state estimation, because you can begin to wrap your head around it. As Carl likes to say, the whole ocean is just too much for anyone to understand. That's what, this is what Ann and Patrick and many other people have been working on. The work is done in Austin, and I think, the LLC 90 grid is shown here. This is what we have for ECCO version 4. So in the Arctic, our grid spacing is about 13 kilometers or so. Oh, sorry, 30 kilometers or so. But in the LLC 270 setup, it is considerably smaller. Grid spacing is 13 kilometers. So, for example, we just wrote a paper looking at a similar resolution setup for around Greenland, 13 kilometers. Okay. So one of the things that they had great success doing was constraining the model data misfit with sea ice extent. So this is what this is showing. Break the Arctic into different basins. And then this is the first one, this is the first guess. This is the so-called red curve, first guess, so every basin has a misfit, whatever, is big. And then what they've achieved now is a very small misfit. So they've gotten blue curve on the sea ice extent. Also meant to be shown here is the climatology of sea ice. In the northern hemisphere, black is the data, blue is their first guess, and then their best solution here, not to be confused, is red. So great success. So getting sea ice is great, but for oceanographers, maybe the more interesting question is how is the Atlantic water changing, the circulation changing in the Arctic Ocean? Of course, we know the Atlantic water coming into the Arctic Ocean comes in through Fram Strait. So we look at Fram Strait because there's a famous mooring array across Fram Strait. So that's what they did. They look at Fram Strait. Okay, I'll show you where Fram Strait is in case you don't know. We look at Fram Strait, depth and longitude, and here in color is a representation of temperature. So here is the warm Atlantic water flowing into the Arctic. And I don't know if this is the data or the model. Some people, but it's probably the model. And it's an estimate, and here, because there are a mooring array with observations, this plot is meant to indicate to you that the model is a much better constrained to the data now. The model data misfit squared cost is much smaller. So, and this is a really cool plot. It shows the temperature at some of the temperature loggers on the moorings. At three different moorings, or temperature, salinity, and velocity. At one of the moorings, red is the state estimate, and blue is the mooring. So it's a very ballpark. Something that we can do with the state estimate is to quantify water mass volumes, water mass volume derivatives. So with the Martha paper, that was like a heat budget analysis in a fixed volume box. But you can also define a water mass through TMS, right? So then you can ask the model, how much water do you have of this water mass? And then you can measure that changing through time. The water mass volume change through time. So, for example, like mode water transformation rate is a famous example. But here in the Arctic, the transformation does not through the atmosphere, it's through lateral mixing, dipycnal or isopycnal mixing. And what Anne is showing here is this is the kind of side down view of the Arctic Ocean. So here's the Greenland, and so here is Greenland, and here is the Russian Asia. That's over here. Okay. So the color blobs here is the volumetric edge of several different water mass types, which is cool. She believes that these water masses are well represented because we have map data, of course, in the Arctic, but this is a measure of the misfit to ITP ice type profiler data. And then what's cool is that not only can she quantify, I cut out the slide because it's too complicated, not only can she quantify the changes in the water mass volume, so you can diagnose the reason why, and then of course you can make a full movie showing, because it's just getting latex, show a movie of the boundary, the volumetric boundary of these different water masses. So like I said, you can diagnose why the water masses are being created, look at seasonal processes, look at interannual variability. So it's a great example of using this ECCO machinery for a focused regional study. And it has many applications, and we'll talk about them in great depth. But it's been used by a lot of people, which is cool. Okay. I'm going to skip, I have to skip this, the Matthew stuff. So Matt Maslow will be here week 2. He and his colleagues work on something called ECCO and other regional products, but I have to skip it for time.
Yeah, and we will, again, Matt will actually be here next week, and he has a dedicated session on.
Yeah, sorry. So, yes, sir.
Yeah, just a quick question. When you do a regional state estimate, does the boundary conditions became like something you can adjust?
Yes. 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 David?
Okay, this is sort of a map of where you think it's most reliable versus least reliable. So, for example, in the Arctic, it's difficult to use, satellite data for oceanography because of the ice cover. So, is it some sort of like a picture version of that?
Of where we think the state estimate is
Yeah.
most reliable?
Yeah.
Good question. Let's talk about that online.
Okay.
Because I pressed, but Anne's the person to ask. Okay. After this, we're going to go to the computer lab. Okay. And yeah. Oh, I'm sorry. I didn't see you in the show.
No, sorry to interrupt. You might have introduced, but I missed it. I don't see what when forcing field, the wind and fluxes, or the forcing field you used for all the versions.
For the first, well, for all the, I'm sorry, I can't speak for all the versions.
I mean, just your version 4, version 5.
Okay, for version 4, version 5, what was our first guess?
Integrate.
ERA integrate. Oh, reanalysis. Okay.
Yeah, it's a reanalysis. It's not OA flux. It's not, yeah, it's ERA. And then for version 5, when we first started that one, I think we used JRA.
Also, you did a good job, and I'm keen on using it.
Oh, yes.
So for this one, for your 1/3 degree version 5 alpha version, did you say it's available now already?
Yeah. Yes.
But the official release is by the end of the year.
Correct.
So do you have anything online, or,
Yes.
or you can? Oh, okay. Oh, right, that's good.
Yes.
But I mean, it's a really an alpha version, right? So is it carefully vetted to really?
It's not officially released. It's online. It has the version alpha.
Please be careful.
Oh,
Yeah.
be careful. Okay.
Yeah.
But
Alpha means pre-release.
official release.
If you buy an alpha release of a video game, it will crash. If you drive an alpha version of a Tesla, it will burst into flames. It's alpha. So it just means probably all right.
Or max.
Goodbye? I don't know about that. But it's probably all right. Just we have to keep in mind, we haven't given it the official imprinted golden seal. but be careful. Okay, so we're going to go to the computer lab, and we're going to have a chance to look at some of the output. Some of us use Fortran for our analysis. Some of us use IDLab. And then I got tired of going onto C and not having a license, and then not being able to do things, and then fighting the JPL for the license. So I said, enough. And I said, I will do IDLab. So I'm not disparaging MATLAB, and I'm not disparaging IDL. And for people who are crazy enough to use Fortran for your analysis, you're awesome. But what we have, different people have developed different tools. So one thing that we have is a toolbox called the GCM Faces. GCM Faces works for MATLAB and Octave. So I think Octave is like a free clone of MATLAB. And then, we'll talk about that in a second. And then we have some tools recently developed in Python. So GCM Faces was developed by Gail Berger at MIT in MATLAB. And it's a toolbox, very powerful toolbox, that has these built-in routines where if you point it towards the model output, you can do very easily some complicated calculations. Okay? So it knows about, the key thing is that it knows about the model grid. It knows how it has a cap, it knows it has these faces, it knows how the faces are connected to each other, it knows about all that. It was built to make that easy. And like I said, available for MATLAB and Octave, and Tim will verify that this is installed, that the students, everyone can use it in the computer lab. Okay. Gail unfortunately couldn't be here, but there is some documentation for GCM Faces, and there's also something, I have to say, this kind of a sequence of there's like a little program that he wrote where if you point it towards the model output, it will make all these calculations for you, so then you can look at how that's done and then reverse engineer and figure out how to do it yourself. Good luck with that. I personally used it for many years, and it was very useful. So then for Python, we have a couple different tools. One toolbox is called ECCO version 4Pi. And its raison d'etre is to make it easy to read the fields and plot the fields and do some analysis with it. People have been contributing to it, Tim, for example. And this ECCO version 4Pi library is, we'll have access to it in the computer lab. And as we were writing that, okay, what happened was I wanted to learn Python, so I started doing this, and I was like, as I was doing it, I figured I would write it all down and make a read the docs notebook out of it and the library for it. So we have this thing, ECCO version 4 Python tutorial, which is not 100% complete, but it does go through capabilities of this tool, and it's available and it's online, and it has these different things that show you how to do it, how to use the package and to do some calculations. And a thing that's got me very excited about this format is it has something called a Jupyter Notebook. Some people are shaking their nod in their heads. Who here does not know what a Jupyter Notebook is? Please raise your hand. 1, 2, 3, 4, 5, 6. Okay, like a quarter of you or so. Jupyter Notebook is like an interactive terminal in MATLAB. So you go into MATLAB, you open it up, and you can start typing, doing calculations in it. So Jupyter Notebook is like that, although it's like kind of a web page. And then the computation is being done on some your own machine or some other remote machine. So all of the tutorials were written in this Jupyter Notebook format. You can open the notebook, and then you can read the material. And then you can also execute the commands within it and make the plots, and you can see the numbers. And you'll see it all very soon in the lab. And then I have to say that this ECCO version 4 Python library is like so many other libraries. It builds on other people's work. So the most important two tools that it builds on, proximate tools, are XMIGCM and XGCM, which are helpful for reading and output. We'll learn more about that. And Tim, what am I missing? Excellent. So when we go to the, I'm going to transition now for us. We're going to go to the lab. We'll give you some questions. Then we go to the lab, and then we're going to get set up on the TAC supercomputing system. And we're going to see if we can log in and do all that will be explained. And ideally, if you want to start looking at looking at state estimate with MATLAB, you can. With Python, you can. So then that'll be kind of like the beginning of our hands-on time together. Before we move on, you guys have any questions about my talk before we get going?
Okay, so just a comment, the lab is a much smaller space, and there are not, I don't think there are actually enough computers. So what we'll have to experiment a bit on how best to do this. Maybe for a start, what we can do is that we just team up in pairs of two. But the thing is that the capability that we have is basically set up to run from any of your laptops. You use it, access the product, do these calculations, and also efficiently, because under the hood, each of your users has one node, so 48 cores available to do these things efficiently. So I think we'll see today how the lab space works and how we best take advantage of it, and then we'll take it from there. So be patient for today.